Very good. Welcome. In last class, um, we started talking about the subject of information geometry. The goal here was to recognize that what we are dealing, whenever we're doing any kind of inference, is dealing with families of probability distributions, and we would like to be able to pick one or a few or something, one probability distribution from among many. So we have a statistical manifold, a space that is composed of probability distributions. And we would like to know the structure of these spaces. In particular, we want to get to the point where we can say, we can establish a measure of how much we can distinguish one probability distribution from a neighboring one. We would like to have notions of curves on these spaces, have notions of vectors, the tangent vectors to curves, have a notion of distance, have a notion of volume. So in order to have the tools to do our inferences more efficiently. So let's continue with that. Let me bring up my digital tablet. So what we would like to discuss is the notion of distance and volume in curved spaces in general. The issue here is that whenever you have a curved space, here's a curved space, uh, there is in general no notion of distance between 2 points. There is no notion of the length of the curve. That is a structure that we have to impose on the manifold from the outside. We have to say there is something in addition to just having this set of points, there is something extra that tells us that, say, these 2 points are much farther away than, say, those 2 points. The notion that the length of that curve is longer, bigger than those two. And I'm on purpose drawing them, saying it the opposite way you actually see it on the picture, right? Because just because this looks shorter to you than that segment, because it's written on the flat geometry of the digital tablet, that does not mean that in reality, for the statistical manifold, this one is indeed shorter. It may very well be longer. So we want to have the tools to talk about those things. And so what are the basic idea that what we're going to do, the basic intuition and idea for all of this is that we want to introduce a notion of distance. And the way that is done when you have a curved space is you recognize that on any sufficiently small region, a space looks flat. So if the space looks flat, then uh, we're going to say it is flat, and we're going to start using the standard notions of geometry associated to flat spaces. So in detail, how do we do that? The whole idea is going to be to say, look, let's look at a sufficiently small region. If the region is sufficiently small, then what we're going to do is start with some arbitrary coordinates, arbitrary generic coordinates. Here are the arbitrary coordinates, and we call them XA. So here we have X1, and there we have X2, and here we have a grid of these arbitrary coordinates. Once again, just because they look curved and it looks that these are not right angles, that doesn't mean anything, okay? These are just coordinates. There is no notion of distance yet. Now, if uh, we want to if we want to add a notion of distance to this space, the way we do it is we switch to a new set of coordinates. Let's call it AXA, but now let us distinguish them with a hat. And how do we do the change? The change is done in the standard way where we say, look, if you have a small displacement in the new coordinates, this is going to be given by these fancy derivatives, dxa, or we're going to write it in terms of this transformation matrix, dxa, where it is implicit that we're summing over the index a. Now, if the manifold doesn't come with a metric, with a distance, notion of distance, and you want to add one, well, you just go ahead and add it. But clearly, there are many, many different ways to do it. What we're going to do is, when you switch to the new set of coordinates, and I never told you how precisely you pick them, you just choose to this new set of coordinates, then we're going to say that in these coordinates, the notion of distance is that of Euclidean space for any sufficiently small region. So we declare that in the XA coordinates, the metric is Euclidean. Yeah, I hope you appreciate that we could have switched to a different set of coordinates and declare that one Euclidean, right? If it is Euclidean, then we do have a notion of distance, which we understand, which is given by Pythagoras theorem. Here we have Pythagoras theorem in terms of the in terms of the hatted coordinates. These are called normal coordinates. The normal coordinates. Uh, so the basic assumption we're making is that there is going to be some coordinate system in which in the vicinity of any particular point we can have a system of coordinates that's a nice orthonormal grid, and so we can use Pythagoras theorem. So now if we return back to the old coordinates, these are the generic coordinates, then what does Pythagoras theorem look like? Well, it's very easy. We just write out our expression for the metric, the Kronecker deltas that we have here, the metric tensor in normal coordinates. Substitute the xa, which is given by this expression. Maybe I should write it like this. So dx, here's dxa. So I have written down dxa hat. Here is dxa hat. Now I'm going to write down dx b hat. Here is, so this is added there, b hat, dxb. Once again, the power of doing these um, summations is that here, right here, we have like one sum over a hat, another one over b hat, another one over a, and another one over b. Plenty of summations there, but the notation is pretty compact. This object here, in which we're just adding over the a hats and the b hats, is an object that ends up having two free indices. This is what we're going to call GAB. And so now the expression becomes dl squared GAB dxa dxb. This object here is called the metric tensor, and this object here is the square of the length of a short segment. Now, once again, and this is the important thing, the assumption behind the Riemannian space is that locally it's flat. So if it is locally flat, you can always go to coordinates that locally look Euclidean, and for them the metric would be known. Now next you transform back and you have the metric in generic coordinates. Now the length of a this is the length that's for an infinitesimally short segment. So the length of a curve if you have a curve like so, here is the curve, the coordinates are given in terms of some parameter. The length of a curve is going to be, you integrate over the dl's for successive short segments along the curve. So you start from some initial lambda to some final lambda, initial lambda to some final lambda, and you integrate this. And the way we do this is we take the dl, which is the square root of dxa dxb, and we integrate from the initial point to the final point. We just add the dl's, and the efficient way to add these dl's is if we know what the equation for the curve is, we just differentiate this to find dx d lambda, divide by the lambda inside the square root, and multiply by the lambda outside. So if you know the metric tensor, you can now compute the length of any curve. Please notice that we never really have a formula for the distance between 2 points. What we do have is a formula for the infinitesimal distances between 2 neighboring points. And from that, we have a formula, I've just written it down here, for the length of a curve. If you want to have the distance between any 2 points, then you have to go through the additional exercise of figuring out among all the curves that join those 2 points, which one is the shortest. So that's another part of the exercise. So this is why this is called inferential geometry, because the actual formulas you have for everything is formulas that tell you what's going on infinitesimally small regions that are sufficiently small that curvature is negligible. Very good. So that's for distance. Now we want to do exactly the same thing to compute volumes. To compute the volume, we're going to proceed in exactly the same way. We're going to say, look, if you want to compute the volume of a small region, you go to normal coordinates. In normal coordinates, we know exactly what the volume is going to be. It's just the product of the size of a tiny cube. So this is for an n-dimensional volume. We know how this works. If you now want to figure out what the volume looks like in generic coordinates, what we have to do is we have to transform this volume here to the new coordinates, to the old coordinates, the generic ones. So in particular, for example, if this were like dx, dy, dz for Euclidean space, we might want to go to generic coordinates that happen to be spherical, r, theta, phi. How do you do that? You do that uh, with a Jacobian. So we have to figure out what the Jacobian is for this transformation, like so. That's what we have to figure out. And this Jacobian is the determinant of the matrix. Let me write it twice. The matrix of the normal coordinates, the ones that are nicely orthonormal to each other, um, dxa. So that determinant, which is the determinant of this matrix. So that's the Jacobian. So if we want to compute what this volume element is, we need to have that Jacobian. And how do we do that? We go back to this expression here. Let me rewrite this expression here that tells us how G, which was obtained here from the metric tensor, has the identity matrix and X matrix. This is contracted here, A hat, A hat. So this is like a matrix product. And then the B hat and the B hat is contracted too. So this is the AB element of the product of three matrices. So let's just do it. So to calculate this Jacobian, we're going to use that GAB, the metric tensor, is the product of three matrices. Now, if you remember from linear algebra, the product, the determinant of the product of two matrices is the product of the determinants. That's one of the beautiful properties of determinants. It's one of the reasons why we care about determinants. Very good. So let's take the determinant of these three, of this matrix equation here. On the one hand, we have the determinant of this matrix, which in principle we know what the matrix is, right? By now, in principle, we know what the matrix is, so nothing prevents us from computing the determinant. Then we have the determinant of 1, the determinant of the identity matrix. That's the first matrix being multiplied here. Then we have the determinant of X, the transformation matrix. And then we have the determinant of X again. So what this is telling us is that the determinant of X, which is the Jacobian we want, is equal to the square root of the determinant of the metric tensor. The notation we're going, and this finishes the problem. We got it. We're done. So the notation we're going to use is we're going to call the determinant of G. Let me write it here. We're going to call it G. So whenever you see a G, you have to be very careful. Am I talking about the metric tensor or the metric matrix, the metric tensor, or am I talking about the determinant? In general, there is no problem, no risk of confusion, but it's one of those things that you have to be aware of. So this is the definition of little g is going to be the determinant of the metric, and this guy therefore is equal to g to the 1/2. So conclusion, the volume element is going to be given by g to the 1/2 dx, and where this just refers, this is, okay, notation or language. This particular object here is not the volume element. This is just the product of the differentials, right? Uh, that's not the volume element. The volume element involves this Jacobian. So as an example, suppose that you have, let's do it in the next page. Not too much room here. Okay, here we go, example. Nothing prevents us from using these ideas when the space is like really flat. So suppose we have Cartesian coordinates and we want to change and use spherical coordinates. When you have spherical coordinates, the length, so let me write down spherical. When you have spherical coordinates, and by spherical coordinates I just mean the usual ones, are theta, and if you project down, the azimuthal angle is phi. Right? This is the connection between the Cartesian coordinates x, y, z, and r theta phi. So we go from x, y, z to r theta phi. Pythagoras theorem tells us that if we are in normal coordinates, the Cartesian coordinates, so normal coordinates, what are normal coordinates? It's just coordinates that are locally Cartesian, but only for a small region. Here we go. That's Pythagoras theorem in the hatted coordinates. In spherical coordinates, Pythagoras theorem looks like dr squared plus r squared d theta squared plus r sine theta squared d phi squared. So this is the object that we're going to write as GAB, dxa, dxb, where dxa takes the values r theta phi. So what is the metric tensor here? Basically, you just read it from the length element. There are the r squared, the theta squared, the phi squared, so that means that there are no cross terms. All the terms you're going to get are along the diagonal, and so there is the term dr squared has a coefficient of 1, the term d theta squared has a coefficient of r squared, and the last term d phi squared has the coefficient d r squared sine squared theta. Everybody else is 0. So when we compute the determinant, what we call G, just compute it. It's very easy because it's diagonal. So it's 1 times r squared times r squared times sine theta squared. So that's what G is. And this tells you that the volume element which is the square root of g multiplied by dr d theta d phi. So that tells you something about how to compute these volume elements in clever ways in arbitrary systems of coordinates. Just figure out what the metric tensor is and you're done. Here's another example, and this is the example that's going to be of most value to us. We're going to do more of these, but basically, what is a uniform distribution? A uniform probability distribution. A probability distribution that's uniform, that does not mean it's constant. By uniform probability distribution, we mean a probability distribution that assigns equal probabilities to equal volumes. So equal probabilities to equal volumes. So if you have a space of thetas and you want to assign a probability distribution that is uniform, we first need to find out what the metric tensor is. Then the probability distribute. This is the probability density, and then here we put the d thetas. So this is the probability, the total probability in a small region defined by d theta 1 and d theta 2, right? So this is the probability within these small coordinate intervals. So this is going to be uniform if this probability is proportional to the volume of that region. So we have to write g to the 1/2, find the metric tensor, find the determinant, g to the 1/2, and then like so. If you want to find the total volume of a region, so here you have a region, a funny region, then the total volume of the region R is going to be, of course, g to the 1/2 dn theta integrated over R. And if the distribution of probability is uniform, then the probability of the region R has to be proportional to the volume of the region R. Now, why do we care about these uniform probabilities? Well, a uniform probability is the closest thing we have to describing a situation that's very symmetrical. I have no idea what is the true value of theta. I'm going to say that the probability that it lands in a certain region depends on how big the region is. So this is our best candidate for what rather maximally ignorant probability distribution would be. So this here is a good candidate for what a prior might look like in a certain space. The fact that you have a prior that is uniform does not necessarily mean that you're going to get good results. Good results in inference depend always on whether the information that you have incorporated into your inference process happens to be relevant to the particular question you're asking. So So whether this knowing what a uniform probability distribution is going to be useful or not is one question. Uh, the assertion that's being made here that information geometry allows us to make is that there is a nice uh, concept of what the uniform probability is. Whether the uniform probability ends up being useful or not, that's another issue. But the uniformity is actually guaranteed once you have a metric tensor. Very good. Uh, I started this whole exercise here of talking about distances and talking about lengths by saying that we're talking about generic curve spaces. Generic curve spaces do not come with uh, a pre-assigned metric tensor. You have to sort of do that by yourself. You assign a metric tensor to the space. You hope you do it right, and from then you proceed. So, for example, when you're doing general relativity, you have these pseudo-Riemannian spaces, the spaces of general relativity that have some minus signs in the metric tensor. In any case, you have these spaces, but you do not have a tensor. You need to actually make a decision as to what is the tensor that you're going to assign to your space. And typically, you do not know. You have to say, well, I'm dealing with a situation that is spherically symmetric. For example, the space-time that surrounds a spherically symmetric star. And so let us use that symmetry and try to figure out what that geometry might be. So you have to sort of make decisions about what particular type of space-time are you talking about. Is it spherically symmetric, or is it wiggling, or is it expanding? And so the criterion we use in most of those situations to figure out what the metric tensor would be to solve the Einstein equations for gravity, right? In general, you don't have rules for doing that. You have to figure out what it is you're talking about. Very well. It turns out to be the case that there is an exception to that rule. The exception is precisely statistical manifolds. And the part of the reason why statistical manifolds are so special is that uh, when you're talking about a generic curved space, the points have absolutely no structure. They're just totally dimensionless points. End of story. Uh, but when you're talking about the statistical manifold, there is an incredible amount of things that you already know about what each point is going to be. Each point is actually a probability distribution. So if you know that the probability distributions are multinomials or Gaussians or things like that, then that additional information may help you pinpoint what the metric tensor has to be. This is a highly non-trivial assertion. Um, But it is nevertheless true. Statistical manifolds are special. They come with a metric tensor that's hardwired into them. You cannot, let me say it differently, you cannot take a statistical manifold and assign any metric you want, because if you did, you would be in principle violating the very idea that you know something about the points here, namely the probability distributions of one type rather than another. So how do we even get to approach the problem of these unique metric tensors that are applied to statistical manifolds? Let me get back here to the end and let me start discussing that. I'm going to do a first try at figuring out a statistical, uh, the metric of a statistical manifold. So we're going to have a few derivations of the metric tensor. I'm going to derive the same thing in several different ways. And in the lecture notes, you're even going to find 2 or 3 more ways to do it. And the part of the reason for this peculiar exercise of deriving the same thing over and over and over again is that I'm going to derive the same thing over and over again, coming from rather different directions. And in that way, you're going to start getting an intuition for what it is that the metric tensor is actually doing in the case of statistical manifold. Then in the lecture notes, there will be a very long session in which we actually prove that that metric tensor is unique. I'll talk a little bit about that later in the lecture. But we're not going to produce that derivation in detail. It's just too long. I'll let you play with it in your own time. So the first derivation, the derivations of the information metric. The first derivation is actually extremely intuitive. It is designed to give you an intuition of what these metrics are actually doing. And it goes like this. Suppose that you have a set of parameters, a family of distributions. Here is the family of distributions called the family, it's a probability of x's and given parameters theta. So that's the family. So this is the statistical manifold. We are going to use as coordinates. We can use as coordinates of a point that we're going to call theta. We can just use these parameters theta. And there may be several of them, so this is multidimensional. Very good. The first derivation that we're going to use this is from the notion of distinguishability. What we want is, imagine that we have several thetas, and here we have the probability distributions, and we have one probability distribution. I'm sorry, bad picture. We have, this is x is the variable that you are uncertain about, and here we have the probability distribution that corresponds to x and the parameter theta. So this whole probability distribution is labeled by theta. And this other probability distribution has a slightly different value of theta. Let's call this delta theta. So the question is, can we distinguish these two probability distributions? In fact, this is the problem that Fisher, the biologist statistician that first introduced the concept of uh, measures of distinguishability, uh, Fisher was very interested. He was okay. Fisher, an interesting character. He was a biologist. Uh, he has been considered one of the most important biologists of the whole 20th century. What he accomplished was he brought mathematics and statistics to bear on issues of the theory of evolution of Darwin. So the question became, can we actually demonstrate the premises or the ideas behind the theory of evolution using sophisticated methods of statistics? And so one of the things that he wanted to do was the following. Um, Suppose you have different birds of different, and the size of their beak is called X. And so when you're in one of these islands in the Galapagos and you want to, you go around studying your birds, you measure their beaks and you get distributions, right? You get birds of all types of, with all types of beaks. And so the question is, once you have bunch of points here, the question is going to be, are there two distributions or just one? Can you tell that you have one species with a certain variance and another species with a certain variance? Or is there just one probability distribution that describes everything with a larger variance? So this is the kind of thing that he was studying, and he eventually came to the notion that what you want to have is a measure, a number, that tells you whether two probability distributions can be distinguished statistically. So how do we invent a number that tells you whether these two are different? Okay, so I'm going to do it wrong 2 or 3 times so that you see what the problem is. Suppose that we want to figure out our delta and just take the difference. Clearly, if the probability distributions are not the same, these numbers do not match. Now, what's wrong with this number? Well, one of the things that's wrong with the number is that this number, for a given x, it tells you the difference between uh, the probability distributions at one point or another or another or another or another. Okay, here we have the first problem with something like this. Problem. This is not one number. It is one number for every value of x. So this is many numbers. One number for every x. So how do we fix this and say, no, 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 we have to somehow combine all of these numbers to obtain just one measure of one number that measures distinguishability. So one possibility would be, well, take the same thing. So that was my first attempt. This is going to be my second attempt. Take those numbers, and just add them all up. Okay, well, this now smells much better because at the very least, this is a single number. But immediately, if you think for about half a second, you start realizing that if these are probability distributions, this is the integral of the probability distribution over all x's. The first integral is 1. The second integral is 1. Sorry, this is equal to 0. So that does not work. So doesn't work either. So let's try something else. So next, we invent yet a third number. Let's call it delta 1 again, once again, in which we do the difference. This didn't work. So let's try it a little bit better by saying, okay, how about if we do the relative difference? Because after all, when you have here a difference between those 2 points, the difference here might be a factor of 2. But if we look at the difference back down here, this is like almost 0. And the other one is like 10 to the minus 3, but this is 0. Let's assume the 0 is like here, right? So the difference back here is huge. Here it might not be that big, just factor of 1.5 or 2. But the difference here is huge. If you have a single object here, you know immediately it's not going to be part of that family. So let us look at the relative difference. Well, okay, we have the same problem that this is not one number, it's many numbers now. So, okay, it's many numbers, one for each value of x. So what Fisher proposed is that let us not take this number and just add them all up. Let's take the average of this. Consider the expected value of that quantity. Now, what is that expected value? We're going to do dx. We're going to do p x theta to compute the expected value. And now we do the relative difference. Minus px theta. Very good. Now you realize that we're in trouble again, right? Because this p cancels that p, and then the integral of the first term is 1, the integral of the second term is 1, this is still also 0. So this does not work either. But now we're going to say, oh, look, this quantity doesn't work because, well, what's going on, you could imagine, is that this quantity that appears up here is just as often positive as negative, right? And so that's why on average it just vanishes. But what if we square it? In fact, because this is the same as, let me write it like this. This is the same as uh, the average squared, because this object here is 0. This is a variance, right? This is this object here minus the expected value of the delta squared, like that. This quantity here is a variance. What that means is that it is positive. Being positive, and actually you can also see that when the delta theta is 0, this quantity here is 0. It's positive and it's equal to 0 if and only if the delta thetas vanish. So this quantity here has all the properties you might want of a distance. It's always positive and it vanishes only when the two probability distributions are right on top of each other. They are the same probability distribution. So this is what works. Okay. This is the notion, the measure of distinguishability that we want. So let's just clean up our mathematics a little bit. We're going to write this delta, which is the delta that appears up here. Up here, we're going to do the following. We're going to simplify this expression by Taylor expanding this expression here. And so we have 1 over px theta. When we do the Taylor expansion, we have the first term is p given theta plus the derivative of p v theta delta theta plus and so on. So you see here I'm just Taylor expanding the first term here. Zeroth order term, first order term linear in the thetas. There is a summation here to indicate that we're taking all the derivatives. And then we subtract px theta, which is the last term that appears here. This term cancels that one. And so what delta looks like is the derivative of p with respect to theta divided by p. This is the derivative with respect to theta of the log of px theta, all multiplied by theta. When we do the expected value of this quantity, of the square of this quantity, what we're going to have is an expected value, then the derivative of the log of p with respect to theta, d theta, and then there is of course the d theta a, and then there is this where that quantity delta comes in squared, so there is a second term, p x theta d theta b, and then multiplied by d theta b. And so this is exactly of the form you expect if you have a metric tensor multiplied by d theta a, d theta b, right? So this object that appears here, this is the metric tensor. This is called the Fisher Rao information metric. It was originally proposed by Fisher in 1923, I believe, as a measure of distinguishability. It was the Indian statistician Rao in 1945 or so who realized that this was a metric tensor. And this is amazing because the moment you realize that you have a metric tensor in the space of probability distributions, you can do all sorts of things. You can compute lengths, you can compute volumes, you know what a uniform distribution is going to be. You can figure out all sorts of other things like curvatures, and you can really bring in all the machinery from geometry to do inference. So this was very important. Rao's contribution is absolutely essential here. So this is what the metric looks like. P, and then the log P d theta, the log P d theta b. Clearly, there are two indices, A, B. If you change coordinates, instead of using thetas, you use theta primes. If you change coordinates from thetas to theta A prime, then the derivative with respect to theta A is going to be written as you differentiate with respect to theta A prime, and then you differentiate theta A prime with respect to A. And this is the quantity that we have been calling x A prime A. So when we substitute this d theta A here, what we're going to have is, let's just write it out. P, I'm not writing the x and the theta. X is the integration variable, theta are just fixed parameters here. D dxp, and then here we have xa, xa prime, d log p, d theta a prime, and then another x b prime b, d log p, d theta b, like so. Now, important, we're integrating over x. These guys here just involve thetas. So these are just constants in this integration. We can pull them out, right? Same thing here. We can bring them out. And so the net result is going to be x prime A, B prime B, and then the term that remains is just the same formula that you had for the information metric before, but now with primes. Oops, there is a prime here missing there. Uh, and so what we have just proven here is that the information metric transforms under changes of coordinates in exactly the same way you expect a metric tensor to transform. Okay, so this is a tensor. Therefore, GAV is a tensor. Once you have this tensor, you can actually do all sorts of weird things, like scalar products or now this is like really weird because look, if you have a metric tensor and you have two vectors like so, you can, this is what allows you to define what the scalar product between two vectors is. And what are these vectors? Well, these vectors are going to be components, derivatives of various curves in the space. Two vectors are just tangential vectors. And so in a space of probability distributions, you can actually figure out angles. You can do lots of things. Very well. I think that this is maybe a good place to stop. I'll come back in a little while.